Hi everyone, welcome to Module 9, Recursion. Up till this point of the class, we use iteration to solve all our problems. So iteration, in the context of computer programming, it is a process wherein a set of instructions or structures are repeated in a sequence a specified number of times or until a condition is met. In contrast, recursion is a different way of thinking. And when we talk about recursion, we mean it solves problems by using functions that call themselves. So the concept of recursion and iteration is to execute a set of instructions repeatedly. The difference between them is that recursion is simply a method call in which the method being called is the same as the one making the call. That means actually whenever we have a recursion, whenever we use a recursive approach to solve a problem, we mean we establish a recursive call or a recursive function, and we call this recursive function in itself. And we try to solve an original problem by solving smaller identical problems. Well, iteration is when a loop is repeatedly executed until a certain condition is met. So of course, every recursion can be modeled as a kind of loop. That's what the CPU will ultimately do. So if we just look at the recursion definition, or the top definition of this recursion, we can see here, which is hilarious, but that's a good definition of recursion. So if we want to look at the definition of recursion, just to see recursion. Okay, so we try to solve the original problem by solving smaller identical problem. Whenever we have a recursive function, we mean we will call this recursive function inside of its implementation. So that's how we define recursion. And we will see more examples later in this module to have a better understanding how recursive function works, how recursion could help us to solve different kinds of problems. And the application of recursion is vital in computer science. So recursion actually is the backbone of artificial intelligence. And the most important data structure that you will learn in data structure and algorithms, which is the course COP3530. The most important data structure, which is tree, which is a hierarchical data structure. So for all the data structure that we have already seen in this class, which includes the arrays and array list, they are linear data structure. And whenever we talk about tree, it's a hierarchical data structure, and it doesn't exist without recursion. We can solve tree-related problems in iterative way. That's to say, using iteration. However, it will be a very hard task. But if we switch to recursion, we actually could use recursion to solve any tree-related problems in an elegant way. And that's what you will learn in data structure class. Okay. And also, we can use recursion to implement some efficient sorting algorithms. So in the previous module, you have already learned basic sorting algorithms, which include the selection sort, insertion sort, and bubble sort. All those sorting algorithms you learned in CS1 actually are the basic sorting algorithms. And they are like big O(n) square time. So if we want to implement more efficient sorting algorithms such as quicksort and merge sort, we would like to use this recursion. We would like to use recursive approach. So let's just give you a bit more context here. So in your project 3, remember when I asked you to implement the sort pacuri method, you are asked to, some of you like implement using arrays.sort, and some of you may use collections.sort. And those sort function are built-in function inside of the arrays library or collections library, but they, the programmer who implements the sort method inside of these two libraries actually use a quick sort, which will use this recursion kind of approach to implement the sorting. Okay, so the quick sort and the merge sort are the more efficient sorting algorithms that take big O n log n time. And when we implement these two efficient sorting algorithms, actually we need to use recursion. And also, recursion could be broadly used in all the puzzle games. And there are a lot of applications will use this recursion, the recursive thinking to solve different kinds of problems. So the uses of recursion is uncountable. That's why we want to learn recursion in this module. And let's just dive deeper into to see what recursion is. And let's just look at very simple example of recursion, how we can use recursion to solve a simple problem. So recursion is the repeated application of recursion. And recursion is a method solving a problem while the solution depends on solutions to smaller instances of the same problems. So recursion solves problems by using functions that call themselves from within their own code. And this approach can be applied to many types of problems. And whenever we talk about recursive algorithms, we talk about this algorithm actually reference itself as part of the solution. And we can break this recursive algorithm into two parts. The first part is the base case. And the second part is the recursive cases, where what we also know as the reference relations. Okay, so whenever we talk about base cases, we say that for a recursive algorithm or a recursive function, it could have one or more base cases, meaning inputs for which the function produces a result trivially without recurring. In other words, we can think about the base case is a simple case of the problem that we can answer directly. We don't need to call the function itself. We can just solve it directly without any recurring. Okay, and when we talk about recursive relations, we mean that the inputs for which the program recurs, the program has to call itself. Okay, so now all those concepts are abstract. Let's just take a deep look at an toy example, the Fibonacci sequence example, to have a better understanding how we can break a recursive function into two parts. The first part is the base case. The second part is the recurrence relations, how we can break this recursive function into these two parts, and which are the very important two parts whenever you try to come up with a recursive solution for any problems. Okay, so now let's just look at our Fibonacci sequence problem. So the Fibonacci sequence actually is the series of numbers. So for example, 0, 1, 1, 2, 3, 5, 8, 13, 21, so that the next number is found by adding up the two numbers before it. So if we look at this one here at the second position, where 0 position, 1's position, 2nd position, 3rd position, 4th position, 5th position, 6th position, 7th, and 8th position. So if we look at this one here at second position, we can think about this. We will get this one by adding up 0 and 1, like 2 numbers before it. If we want to get 2, we want to add up this 1 and 1 to get 2. And for 3, we want to add up 1 and 2 to get 3. For 5, we want to add up the 2 numbers 2 and 3 before it's to get 5, and so on and so forth. So what's the next number after 21, which is the nice number in the sequence? So what should be the next number after 21? Let's spoil it. So we just need to add up the 2 numbers before this number at position 9, which is 13 plus 21. I will get 34 after this 21. So on and so forth. I can get nth Fibonacci number, okay, based on these numbers in this sequence. Okay, so how I could come up with a recursive solution to solve this Fibonacci sequence problem. I want to get the nth Fibonacci number in this sequence. How I get that nth number. So as we said, for our recursive function, the very important 2 parts are the base cases and the recurrence relations. So let's just first look at our base case. So for our Fibonacci sequence number problems, we have 2 base cases. That's to say when the zero's Fibonacci number, which is 0 here. So zero's Fibonacci number is 0. And the first, or the Fibonacci number, that first Fibonacci number is equal to 1 here. Okay, so these are the 2 base cases. Those are the very simple case that you could get the results, get the answer directly without recurring, without call the function, the recursive function itself. We can just get the answer directly. Okay, so we know fib 0. So fib 0 is 0. Fib 1 is 1. So what about fib 2? I know that fib 2 will be equal to fib 0 plus fib 1. For the fib 3, it's equal to fib 1 plus fib 2. And for the fib 4, we could get it. So fib 4 is equal to 3. So we can get fib 2 plus fib 3. We'll get the 3, which is fib 4. So so on and so forth. We can get a pattern here. We can like establish our recurrence relation. That's to say the fib n, the number of the nth Fibonacci number is equal to Fibonacci number at n-1 position plus the n-2 fib number here. So if we look at our so this is fib 5, fib 6, fib 7, and fib 8. So if we want to get fib 9, it should be equal to fib n-1. That's to say 8 plus fib n-2, which means fib 7. Okay, so fib 9 is equal to fib 8 and plus fib 7. So we can establish the recurrence relation based on the pattern that we find in this sequence of numbers. We can see that fib n is equal to fib n-1 plus fib n-2. And you could see here this recursive, this fib function, which is a recursive function. By solving the original problem, we want to see the fib n, we can just call fib n-1 plus fib n-2. We solve the original problems by solving the smaller and identical problems. Okay, so this is the recurrence relation. So we break these recursive algorithms into two parts. The first one is the base case. The second one is the recurrence relation. So whenever you want to come up with a recursive solution, you always have to think about what the base case is for this problem. What should the recurrence relation is. So you have to think about these two parts to come up with the complete solution for a problem using recursion. Okay, so the job of the recursive case can be seen as breaking down complex inputs into simpler ones. So in a properly designed recursive function, with each recursive cause, the input problems must be simplified in such a way, so you can see here in this the picture below here at the bottom, the problems become smaller and smaller and smaller and smaller until eventually we reach the base case and we will stop. Okay, whenever we reach the base case, we will stop. We will not have an infinite loop. We will not have an infinite recursion. So we want to have a correctly defined base case, correctly defined recurrence relation so that we can eventually reach the base case. If you don't have a correct base case where you don't establish a good recurrence relation, you will have an infinite recursion, just like the picture described above here. So you just have the recursion, infinite recursion, because you didn't reduce your problems. You didn't have smaller problems each time. So you will just keep looping, keep recurring, keep calling your recursive functions. So in this module, we will see how we can establish a correct recurrence relation, how we can come up with our correct base case so that we can come up with a good, complete, elegant, efficient recursive solution.